Hello, welcome to session number 5 in the playlist Electrodynamics. And till now, we have been looking at some of the EM simulators, namely the method of moment and FDTD. Now, there is a question which comes to me from students all the time. If they can simulate an active device along with the the passive design for an IC design, and my answer is no, because EM simulations, EM solvers are basically Laplacian solvers, right? And they will not be able to do a charge distribution in a volume, right? So having said that, we have to look for a tool which can do a solution along with the carriers, right? So it would be some form of a differential equation solver, right? So one of them is a multi-physics tool called COMSOL, right? So let's launch that COMSOL, and I'll just show you something before we go into a device. So here we are looking at a basic structure, very basic structure of a MOSFET. Now it can be turned into a complex structure, and you can build in any advancements into it, right? But what I want to do is for you to be able to create this structure and do doping and doping profiles and be able to simulate the characteristics of a MOSFET, right? Using the device physics, right? So, and you can, in this process, you can learn how a device actually works, right? Okay, so what we are supposed to do now in COMSOL, there are two things you should remember. Okay, one is called the domains, the other is called the boundaries. So domains are surrounded with boundaries. So for example, if I consider the entire volume here of the device, that would be called a domain, right? And then this domain can be a three-dimensional domain. It can be a cuboid, for example, right? So I'm trying to make a device which is going to be a cuboid. Okay, so the entire volume would be called a domain, right? So let's see if this comes up. Okay, so as soon as your COMSOL comes up, you go to the model wizard and you go to 3D, right? And in the 3D, you choose the physics to be semiconductors and say add, and then you can choose a study right at the start or later on maybe, and the study is going to be stationary. Stationary means we are going to have voltage sweeps, we can have current sweeps, but there is no time information, right? So the time information would come into transient simulations, right? So, or time dependent simulations here. And then the other study can be a small signal where you can do the S parameters of a transistors, right? So without any delay, I'm sorry about that, let's dive into it. We just say done, and as soon as we say done, we are presented the IDE of COMSOL. And in this IDE, okay, there are 3 columns broadly you can see if you ignore this message window, right? And the 3 columns are going to be the model builder, which is like a workspace tree, right? And then there is this property inspector or the settings, where you set the settings for various, for the project, for various components and stuff like that. So that is called a properties inspector here, right? You can define various properties, and then you have got a large area which is marked as XYZ global, and this is the place where you're going to draw the MOSFET, a 3D of a MOSFET, right? And then to help you draw this there and to do the simulation, you have this ribbon, right? Now here this ribbon is going to be rarely used in the initial work, and mostly I'm going to use the menu, not the toolbar or the ribbon here, right? So I'm going to do that. Now before we can start a MOSFET device, right, or any device, you should be deciding in your head some things like the geometry, right? So here I'm presenting you a geometry, right? So assume that this is a cuboid and you are looking at a cut section of that cuboid, right? So in that cut section, you are going to see the entire volume, which is going to be the light blue color. This entire volume, okay, this entire volume over here, which is in the background, this would be called the domain, right? So I will make a cuboid for that domain, and the dimensions I'm going to choose is over here, 100 nanometer versus 100 nanometer is the height, 200 nanometer is the width, and then the depth I'm going to take as 2000 nanometer or 2 micron. So the device is going to be 2 micron divided by 45 nanometer. So that will be the physical W by L size of a MOSFET, right? So let's do step by step. Okay, so what we'll do is, let me see if I'm recording. Okay, so what we'll do is we will go to COMSOL and we are going to do certain settings. So first of all, it doesn't have a name, right? So I'm going to say file, save, and I'm going to call this as NMOS 40 nanometer. So I'm going to make a 40 nanometer MOSFET, right? So I'm going to say save, and that name would reflect here, right? So it's saving. So once it saves, this reflects over here. Now global definitions, right? So nothing here. Parameters, right? So let's say if I want to do IV characteristics of an NMOS, right? So I need to specify two voltages. One would be the drain voltage, other would be the gate voltage, and then the 0 volt is a fixed number, so we don't have to define that. So what I'm going to do is I'm going to put here, let's say VD, okay, and this is case sensitive, and then I'm going to put here let's say the initial value, let's say is point, or let's say 1 millivolt. So I can put the units in the square brackets. So in units in COMSOL are going to be square brackets like this, and then I can give a description that this is the drain voltage, right? And then over here I can put gate voltage VG, and that gate voltage I can put here 0.1. Okay, I can put the units as volt, but that's optional, right? And then here I'm going to say this is a gate voltage. Now COMSOL allows you to do a lot of description everywhere, so that if someone sees your design, they would know what you are trying to do. Okay, as far as material, I'm not going to add material right now. It's going to be silicon, right? So I'm going to make a silicon MOSFET. Now component, okay? So now I'm going to name this component as NMOS, right? So that's done. Now I'm ready to draw the geometry, which is the domain. And the domain is going to be a cuboid. As we have discussed, the entire volume would be called the domain, right? Or there may be multiple volumes, they will call them different domains, right? But here there is only one domain, which would be the body of the MOSFET, right? So if I go to geometry, right, and if I right click on it, I can say I want to put a block. Okay, and one more thing you can do before you even put a block, so let me just delete it. Okay, you can fix the units. So as soon as you click the geometry, you have the option to fix the units in which you are going to draw. So I'm going to draw in nanometers. So that's nanometers. Okay, so let's get started. Okay, so here right click, block, and all the units are in nanometers now. So the width I'm going to keep as 200 nanometers. Depth I'm going to keep as 2000 or 2 microns, right? And the height I'm going to keep as 100 nanometers, right? So that is there, and the corner is going to be 0, 0, 0 as a coordinate system corner, right? And at the bottom you will see this will result in a domain selection, right? And if I want, I can give a color also. I can make a color, custom color also. Let's say if I choose a blue one, okay, I can choose somewhere here. That's a green one. Okay, so let's look at the blue one somewhere over here, right? So that's done. and contribute to none. So basically this will result in a cuboid which is going to be a domain, right? And say build selected. So now you got 200 micron by 100 micron by 2000 micron. Sorry, 200 nanometer by 100 nanometer and 2000 nanometer or 2 micron. So this is going to be the space where I'm going to construct the device and I'm going to study its characteristics. Okay, so once you do that, right, all the metal structures, right, which are going to bound this volume, okay, they would be called what you call boundaries. So this is a domain, and domain has got 6 boundaries right now, and in one of the boundaries can also be split into different boundaries, right? So for example, if I want to draw the source terminal, the gate terminal, and the drain terminal, so these are going to be 3 rectangles on the top, right? So let's draw that. Okay, so look at this geometry here first. So this yellow thing, which represents a metal, right? So I'm going to draw this metal as a source contact. So this green thing is a source, and the green thing on the right is the drain. So this 1 is the source contact, 2 is the gate, right, contact, 3 is the drain contact. So these are the boundaries. And then at the bottom, I'm going to put the body contact. Of course, in a complex design, you can put the body on the sides, right? Surround the device entirely with the body. But to keep the thing simple and less time consuming, I'm assuming that the entire bottom is going to be the body. So I have got 1, 2, 3, 4 boundaries which I have to describe or draw. Right, so let's draw these 4 boundaries. So the width is going to be 75 microns, right? You can see here the width is going to be 75 microns, and the depth is going to be 2000. Sorry, width is going to be 75 nanometers, and the depth is going to be 2000 nanometers. Similarly, here the width is going to be 40 nanometers, and the depth is going to be 2000 nanometers. Now, why the width is 40 nanometers? Because that's going to be the gate length. Right? So the gate length is the distance between the source and the drain. So that gate length is 40 nanometers, right? And so I'm constructing a 40 nanometer NMOS device. So let's do this 3 metals on the top. So to draw that, if you go back to COMSOL, okay, so to draw that, first of all you insert a work plane, which is the XY plane, and right now the XY plane is at the bottom. So let's define that at the height, and the height is going to be 100 nanometer, right? So that's the plane. So once you have that plane, you can right click on this plane geometry and say insert a rectangle. Okay, so I'm ready to draw the source or the boundary you want. So this is going to be a boundary. So the width of this is 75 as we have decided, and the height is going to be 2000 nanometer, right? 75 nanometer by 2000 nanometer. Corner is 0, 0, and this will result in a not a domain selection but a boundary selection, because as we discussed, a domain is the entire cube and boundaries are surrounding the cube, right? So that will result in boundary selection. If I want, I can give it a color. So I'm going to give it a yellow color, right? And just say build out. So now you can see I have built this on the top view. It will look like that, and on the cross section it will look like that, right? It will look like 1, which is 17.5 nanometer across, right? And the depth is not known because this is a cross section. The depth is known in the top view. Okay, so the top view says it is going to be 2000 nanometer. Now on the same surface, okay, so let's name this as source contact. Okay, so that's called the source contact. Okay, now every time when you click build all, it's going to build whatever geometry you are trying to build, right? So on the same plane, click once again a rectangle, and this rectangle I'm going to say is a gate contact, right? Okay, and the width is going to be 40 nanometer, right? And the height is going to be 2000 nanometer. So this would be the gate, but where is the corner? So if I go to the drawing, Okay, my origin is on the left side as 0 nanometer, and if I go 75, that is where this first boundary ends. Then at 80 the new boundary begins. Okay, so at 80 nanometer, if you look here, at 80 nanometer it begins and ends at 120 nanometer. So 80 plus 40 is 120 nanometer, right? So I will place that at 80 nanometer. So let's do that. Okay, so here the corner is going to be 80 nanometer. Okay, and then it will result in boundary selection, and the color I'm going to give it is orange color, and say build out. So now you can see that. Now if you want, you can always zoom into to see what has actually happened. So this gap, what you're seeing, this gap is going to be 5 nanometer, as it is in the drawing. This gap between the source boundary and the gate boundary is 5 nanometer, right? So I'm going from left and up to 75 nanometer is my first boundary. From 75 to 80 it is blank. Then from 80 to 120, which is 40 nanometer wide, is going to be my gate boundary, right? Or gate contact, right? So if I go here, that's the gate contact. Now I'm going to insert one more rectangle here, which will be the drain contact, right? So I will name this as drain contact. Sometimes I do spelling mistakes. Okay, so that will be called the drain contact. And what is the width of this? 75 nanometer. And what's the height? 2000 nanometer, right? So this is the top view, if you don't forget. What is the corner? The corner will be 5 nanometer beyond this. So this is 120 here. So 5 will be 125. So if you look in the drawing, 120 over here plus 5 is 125. So 125 to 200 would be my domain, my boundary 3, right? That will be the drain contact. So let's do that. Okay, so let's put here 125 nanometer, and this will result in a boundary selection, and I will give this a color yellow. Okay, and when I say build all, you can see that this is constructed. Okay, you can use a view all to see how it looks from the top view, right? So we have constructed this. Now we also want to construct the bottom side. So if you look here, the bottom is all continuous from 0 to 200 and the depth of 2000, but then the xy plane is at z equal to 0. So let's go ahead and describe a new plane here, new work plane, and that work plane is going to be at the bottom. It shows at the bottom with z equal to 0, right? So we are ready to draw. So we will do a right click and say rectangle, and we want to call this as body contact. Okay, so that's a body contact. The width is going to be the entire 200 nanometer. The height is going, in this case, is going to be the depth, right, which is 2000 nanometer, and the corners are 0, 0. This will result in a boundary selection, and I'm going to give this a yellow color. And when I say build out, that's built. So that's the bottom side of it. Now if I go to the geometry, and if I say build all, you will see that the entire geometry is constructed now. Okay, so this is the source, this is the drain, this is the gate, this is the drain, and at the bottom, that's going to be the body, right? So once this is done, we are done with the drawing of the geometry, right? So we can keep this aside. So we are done with it, and meanwhile you can just save it. So there is this floppy disk here which says save, and you just save it so that in case of power failure, you don't lose your work. Okay, now the next thing which I see is a material. So as soon as I go to material, I can click on this tab which says add material, and I can add a material from semiconductors, and the top one is the silicon, right? And then say add material to the component. Okay, so once you do that, you can just close this, and the material properties are defined here. And so these are your energy band gap and stuff like that, right? So all the properties of electron mobility, hole mobility, everything is defined over here. Okay, so you have defined your so this is still called block 1. Why would I call this block 1? Let's see. Okay, I can call this one as body. So this refers to the cuboid, right? I don't like to see block 1. Okay, so now it will be called the body. Okay. Okay, so we are done with this. So we have added silicon to the body, right? So that's the domain. Now the next thing is the semiconductors. Okay, now here what we are going to do is the things related to semiconductors, like, so for example we can define a recombination model. Okay, whole electron recombination model. Usually it's a trap assisted recombination. We can also describe the carrier distribution. So there are two carrier distributions here. One is called Fermi-Dirac, other is called Maxwell-Boltzmann. So I'm not going to go into the details of what's a Fermi-Dirac, what's a Maxwell-Boltzmann. You can refer to any physics book. They will tell you, which one will be used, which one, should not be used. So in case of, NMOS device, which is the right one, and in case of PMOS device, which is the right one. So that is over here. This is called carrier statistics, and I'm going to choose Fermi-Dirac. Okay, so I'm done with that carrier distribution, right? And then the solution would be for electrons as well as holes, right? And do you see anything else here? No. Enable physics symbols, equations, nothing. Okay, so once you have reached here, you go to domain or the physics. Okay, in the physics, first of all, I have to describe what is the model for recombination of electron holes in the entire domain. So in the entire domain is this cuboid or a box which is called body, right? So I can basically go here domain and say trap assisted recombination, and I can choose body. So in this entire body, I am going to have a trap assisted recombination of electron hole, right, with a certain relaxation time. So I'm not going to change all those details. Okay, so here again there is a Shockley-Reed-Hall model. So there are different models for your trapping. Okay, so I'm not going to go into details. So once you read device physics, you will know what these are. So I'm going to leave this to Shockley-Reed-Hall model. Okay, so that's done. So once that is done, let's start doing the doping. So the doping is done in the domain, not with the boundaries, right? It is done with the domain, right? So we are going to do with the entire box or cuboid or body, right? So now in that case, okay, let's go back to presentation. Okay, so the background of entire thing. So if I, for example, if I was to remove this guy, so you see the background basically is certain doping, and similarly if I remove this, you see the background is the entire doping, entire background, right? So let me put them back. So that is a background doping, and that is 10 raised to 6 centimeter cube, and that I'm calling as acceptor 1 because this is a p-type material, right? So that will be acceptor 1. So let's go ahead and do that. Okay, so go to COMSOL, and here I am going to add analytic doping model. Okay, and I'm going to choose the body, and the entire body is going to be used, right? And the carrier concentration is 1e16 per centimeter cube. Okay, this is your intrinsic carrier density, Ni, root of Nc and V raised to minus Eg over twice of kT. Okay, so that's Ni for silicon. Okay, so once this is done, I will call this as background dope. Okay, so that's a background doping. Okay, the next thing I'm going to do is another doping, okay, which will be at the bottom, okay, for the body contact. So if I go to my drawing here, you see this one, which is corresponding to this one. This one says body contact doping acceptor 2. It is going to be 10 raised to 18 per centimeter cube. Okay, so this is your acceptor impurity, right? So this is p-type material. So let's go back to COMSOL and let's look at these dimensions. These are going for entire 200 nanometer, for the entire depth of 2000 nanometer, and a height of 30 nanometer, right? So you can choose, you can experiment and choose what you want to do. Now in reality, this would be a P plus contact for the body. So I'm trying to generate a P plus here. Okay, and look at this 10 raised to 18, which is much higher than 10 raised to 16, right? So that is my P plus. So a P plus contact I'm going to create to remove the Schottky effect. So let's go and do the P plus there. Okay. Okay, so I will call this as body doping. Okay, and the domain is going to be the entire body, but then I'm going to specify the box. Okay, and in this box I'm going to say I have an acceptor which is 10 raised to 18, which is 10 raised to 18. The corner is 0, 0, 0. The width is 200 nano. So correct this unit, it's not micro. And the depth is 2000 nano, correct, and the height is 30 nano, right? And the next thing is, this is not going to be an abrupt junction. This is going to have a Gaussian fallover. So basically 10 raised to 18 falls over to 10 raised to 16 with a Gaussian distribution, right? And then I can specify the depth in which this should occur. So I will keep this as 2 nanometer. So within 2 nanometer, I would have a Gaussian distribution of drop from 10 raised to 18 to 10 raised to 16. So there are no sharp or abrupt junctions here, right? Okay, so once this is done, I also say that this is with reference to acceptor 1, right? So this is with reference to acceptor 1. So this is done. So this is going to be my body doping. Now the next thing, if I go back here, is starting at a height of 60 nanometer. Okay, I am going to go to height of 20 nanometer on top of that 60 nanometer, and that layer I will call the spacer. And what this spacer is going to do is going to reduce the leakage from the drain to the body. Okay, so I am going to put a spacer here. Now the width of the spacer is 200, the depth is 2000 nano, and the height is 20 nano, but then the corner is at 60 nano on Z. Okay, so I will call that as spacer. So if I go to domain and say analytic domain, and I will call this as a spacer, and this will be drawn in the domain, which is the body, and this will be a box, and this is still p-type, but here I'm going to put 10 raised to 19. Okay, so this is p plus region, right? And the corners are going to be 0, 0, 0, but here the height is going to be 60 now, 60 nanometer. Make sure your units are correct. Okay, and the width is going to be 200 nanometer. The depth is going to be 2000 nanometer, and the height is going to be 20 nanometer. So I'm going from 20 nanometer height to 60 nanometer height, and then I am going to have a Gaussian at the edges, Gaussian distribution within 2 nanometers. Right, and then I'm going to say that everything is reference to domain 1 or the acceptor 1. Okay, so once I do this, I have the spacer as specified, right? Okay, so later we'll show why it's not showing up here. I will, after I'm done with all the doping, I will do that. So I have put a body dope, okay, and all the units are correct. Then I have done a spacer dope. Here also all the units are correct, and this is 10 raised to 19, this is 10 raised to 18, and the background is 10 raised to 16. Correct? So spacer is done. The next thing is I'm going to dope underneath the channel. Okay, I'm going to put P plus underneath the channel. Now the carrier concentration here is going to change your channel length modulation. Okay, so you need to know the devices. Okay, so yeah, I referred you to my analog circuit design, analog integrated circuit design using ADS, where you will know what is this channel length modulation, and later we will visualize this over here and see what is channel length modulation. So first thing first, if you increase the channel doping, it's going to do two things. One thing, it's going to change your let's see. Okay, so one thing is it's going to change your threshold voltage. Okay, the other thing it is going to do is your channel length modulation. So that is going to decide that. So another thing, let's put this in spacer. Let's put this as 0.5. So I just change of heart, don't worry about it. Okay, 0.5, doesn't matter. Okay, so let's go back to domain, analytic doping, and here put the channel doping, channel dope, and this will be in the same domain, which is body, and this is going to be a box, and this is going to be the same acceptor, which is going to be 0.5 E19. Okay, done. Now the corner is, you can refer here to the drawing. Okay, on the width direction, the corner is going to be at 80 nanometer, right? There is where it's going to start, and the height is going to be 82, right? So the height is 80 and the width is 80, so the corner is going to be at width of 80, height of 80, and z equals 0. Okay, or the depth equals 0. So let's go back here. Okay, so we are doing a box, and we say that this is going to be at width of 80, the corner is going to be 80 nanometer, and it is going to be at this thing of height of 80 also. Okay, so height of 80 nanometer. Okay, so we have the right location now. Now what is the width of this channel? 40 nanometer. So it will go from 80 to 120, right? And what is the depth? It is going to be 2000 nanometer. And what is going to be the height of this? 20 nanometer. Okay, why 20 nanometer? Let's refer back to the geometry and we will see that. Okay, so if you refer back to the geometry, you will see that the height of this green stuff here is 20 nanometer, right? So we are trying to dope this section here. So the height of this is going to be 20 nanometer above 80, so it will reach 100. So the entire length is now covered, right? So we are going to do this height of 20. 80 to 100 is going to range in z direction. Okay, let's go back here. So height is 20 nanometer. Again, this is going to be 2 nanometer. Okay, so again, I would say this is against acceptor 1. Okay, so up till now, everything has been p-type only, right? Everything has been acceptor, right? So now we are done with acceptors. Okay, now if you want to really see that, okay, you have to first define the mesh to be able to see those things, right? So let's go here to mesh, and under mesh section I am going to go to boundary and say free triangular, and I'm going to choose this boundary and say build out. So you see here the meshing is done, right? Okay, now this meshing is not very accurate, so what I'm going to do is I'm going to go to the size, and here I'm going to put in the semiconductor mesh, so not general finish, semiconductor, and I'm going to say finer, and later I'm going to do custom build. So this is what the mesh would look like, and so the meshing is done in this plane, and then I will draw a prismatic cells for this triangular mesh. So in the in the depth direction, it is going to be just a swapped. So that is swapped here, and say build out. So now the entire body is meshed now, right? Okay, so these are prisms, right? Prisms from this side of the body to the opposite boundary of the body. So it's a prismatic cells here. So the meshing is done. So once it is done, you go to study, right click it, and say get the initial values. Okay, get the initial values. So once you click that, it's going to do some things. Okay, so now this kind of looks strange, right? Okay, but what's happening here? Okay. Okay, but you got a rough idea of what I wanted to do, right? Now this would change. This is electron concentration, right? Let's try to understand this. 10 raised to 16, but then I heavily doped it. So this is lightly doped. So let's look back at the background doping. 10 raised to 16, body dope. Okay, body dope is at the bottom. Bottom with the origin is 0, a height of 30. That body dope is 10 raised to 18. And then spacer is 0.5 10 raised to 19. It goes from 60 to 80 for the entire space. And then from 80 to 100, or 20, 20 on top of 80. And from 80 to 40 nanometer wide and the depth of 2000, I have a carrier concentration of 0.5 E19. Okay, so you got an idea what I roughly showed you. Now I need to do one more doping, which will be for the source, right? So for example, over here, that green colored thing which I have represented, that's going to be the source doping, and that's 10 raised to 0.5 into 10 raised to 19, or I can put 10 raised to 19, that's okay. Okay, so I'm going to put 10 raised to 19 here. So its extent is from 0 to 80 in the width, and 2000 in the depth, and 80 in the height. Okay, so let's do that. So I'm going to go here to physics, go to domain, and say analytic doping, and say box, and instead of acceptor I have got donor now, and the donor is going to be 110 raised to 19, correct? And then the corner is 0 0 0, but here this is going to be 80 nano because we are drawing at a height of 80. Corner is 0 0, and the width is going to be 80 nano, right? 80 nano, right? And the depth is going to be 2000 nano, right? And the height is going to be 20 nano, correct? And then this variation is going to be 2 nano, correct? And this is reference to acceptor. Okay, so now we have done a doping, which I will call as a body, and I will call this as a source doping. Okay, so sorry about that. Source doping. So we are done with the source doping. Let's verify. 1E19 of donor, and starting at 80 of height, width of 80, depth of 2000, height of 20, and then Gaussian 2 nanometer, reference to domain acceptor 1. Okay, so this is done. So let's do that again. Study, right click, say get initial values. Okay, so now this will make more sense, right? The colors. Okay, so what do you see? The source is doped. So this, you are looking at electron concentration, right? So this is an n-type material. So at the concentration, it is going to be 10 raised to 19. So 10 raised to 19 is brown color, right? So you are seeing this source doping. Then you can also see this dark blue, which is the spacer, and the channel is dark blue, right? So this is going to be where you are going to have holes, not electrons, right? So that's why it is dark blue. Then at the bottom you see the body contact, right? That's also dark blue, right? So that's somewhere over here at the bottom of the lesion, right? And then there is a space left here where we have to do the drain doping, isn't it? So the next step would be, if you go back to the domain, physics domain, analytic doping model, and here I'm going to say drain dope, okay? And I'm going to choose the body, and here I'm going to choose a box, and here this is going to be donor. This is 10 raised to 19, correct? And the corner sorry about that. Okay, so the corner, you have to see the geometry. So the width wise, the corner starts at 120, correct? Has a width of 80, depth of 2000, and a height of 80. So 120 is the width, height is 80 for the corner. Okay, so the corner is at 120 nanometer, correct? And it is starting at a height of 80 nanometer. So that's my corner. Then it has a width of 80 nanometer, a depth of 2000 nanometer, and a height of 20 nanometer. Just as we did for the source, but now the corner is slightly different, right? The corner is, and then this is going to be 2 nanometer. And then this is with respect to the first one. Okay, so this is going to be a donor, right? So once we are done with this, we can save this. Saving is not required in between, but I save it as a habit. Okay, so let's look at the initial value again. Study, right click, look at the get the initial value. So now the doping profile is done, right? Okay, now this edges are not so smooth, they are jagged. This is because of your meshing is not fine enough, right? Okay, so this is done. Now we have to create the metal contacts as terminals, right? And then the gate contact as a thin gate oxide, right? So we are not supposed to draw the thin gate oxide. We just specify the boundary, which is a thin gate oxide with a certain height. Okay, so let's do that. So first of all, I'm going to describe the source terminal, right? So if I go to physics, boundaries, and say metal contact, okay, and that metal contact is going to be this one. So this, the first thing is going to be the source, right? Okay, so this is source, and in this case the source is tied to the body, so this is also tied. So both of these are tied together as a metal contact, right? And these are going to be at 0 volts, correct? So they are at 0 volts, right? So we will call this one as source body term. So this is a source body terminal, right? Okay, so source and body terminal are done. Okay, so this is the body, and this is the source terminal, right? So this is done. Now the next thing is going to be again a thin insulator gate. Okay, so in this case the gate is going to be the center conductor, so you just select that. That's the gate, which is that in this case 7, and here that has to be applied a voltage VG. So remember, we created a VG under parameters, right, at the start. So that VG voltage is applied here. Now if you are going towards sub 100 nanometer, okay, the oxide is no longer silicon dioxide. Silicon dioxide has a dielectric constant of 3.9, while here high K dielectrics are used. For example, hafnium oxide, which would have epsilon of 25. So that's over here, 25, right? Then the thickness I'm going to keep as 1 nanometer. So the gate oxide thickness is 1 nanometer, correct? And then this is called metal semiconductor. So this will be semiconductor work function. So in this case, I'm going to keep this semiconductor work function as 4.1. I'm not going to change it. Okay, so that's there. Work function for a whole, like for example, when we work with PMOS, this is going to be 4.85, something like that. Okay, so in threshold voltage, again, I will refer you to my this playlist, which is called Analog Integrated Circuit Design using ADS. There you will see what is VD. VD is going to be metal semiconductor work function difference plus your what you call QB0 by COX, okay, plus twice of phi 0, okay, plus QB by COX minus QB0 by COX. So the first term is VT0, the second term is going to be the body effect term. Okay, so if you want to know what that is, you have to go to my playlist called Analog Integrated Circuit Design using ADS. There I have detailed what the threshold voltage is going to be. So that is a semiconductor work function over here, 4.1. Okay, so I will call this as gate contact. Gate contact. Okay, so that's VG terminal. Okay. Now the other terminal is going to be the drain terminal, right? So I'll again go to boundaries and say a metal contact, and I'm going to choose this as a drain terminal, and here I'm going to apply a voltage of VD. So once you do that, it's accepted VD as that, and I will call this as gate terminal. Sorry, so let's name them correctly. So this will be called the drain terminal, right? And this one will be called the gate terminal, not contact. Okay, so we have got source body terminal which is at 0, gate terminal which is at VG, drain terminal as VD. So now we are done with the entire thing. Okay, we are done with the entire geometry creation. We can just hit save. Now the next important thing is, in case of Laplacian solvers, in case of method of moments, in case of FDTD, maybe in FDTD you might struggle with the stability, right? In case of FEM or MOM, you will never struggle with convergence issue. But here, okay, convergence issue is a very big issue. Okay, in COMSOL, okay, it might not converge if you do not do it properly. So mesh settings you might have to play around a little bit. So what I'm going to do is I'm going to do a custom, and this is something which I have figured out here as a number 2510, 1.03, 0.8 and 1.2. So 2510, 1.03, right? Okay, so let's go here. I will say the maximum element size is 25, the minimum element is 10, then the growth rate is 1.03, and the curvature is 0.8. Let's see, the curvature is 0.8 and 1.2. Okay, curvature is 0.8. So this is something you have to play around to really find out a setting where you will converge. And when you say build all, okay, so now you are ready for simulations. Okay, so simulation is called a study here. So now if you see this doping, okay, so this is how your doping is, right? And this is going to be view all. So it's more dense at the place where the current densities are going to be large, right? Okay, so now we go to the study. So here under stationary, I'm going to do extension. So auxiliary sweep for all combinations of your VD and VG. So first thing I'm going to add is VD, because I want to plot the what you call the transfer characteristics to find out the threshold voltage. So from the transfer characteristics, I'm going to get the following information. I'm going to go get the sub-threshold leakage. I'm going to get the sub-threshold slope. I'm going to get the threshold voltage. I'm going to get the what you call trans-conductance. I'm going to get the mobility degradation. I'm going to get the GIDL or gate induced barrier lowering. Okay, so all this information comes from, if you don't know what that is, please again refer to my playlist. Okay, so all that, okay, you can extract from this transfer characteristics, which will be plot of the output current versus input voltage. So this will be the terminal 3 current or drain terminal current versus the gate VG voltage for a given VD. So for a given VD is first thing you have to put here. Okay, so when you say add, so for a given VD, so let's solve this for so here if you click on this, you can specify the range. Let's go from 0.8, okay, in steps of 0.1 to let's say 1.2, okay, and say add. Now the next thing is, for all these values I'm going to see the gate, and the gate voltage I'm going to see from 0 in steps of 0.1, correct, and I will go up to let's say 2.5 volts or 2.4 volts, right, and say add. So we are done with that. Now this is the last, this is the run continuation from last parameter. So when you are doing a sweep, once the inner sweep, which is VG from 0 to 2.5 is done, what do you do with the initial value for the next sweep? Okay, are you going to do from the scratch? If you're going to do from the scratch, you say no parameter. Or if you are going to have a certain initial value from the last parameter, you do that, and then reuse solution from previous stage, say auto. Okay, so once you are done with this, just save it. Now the whole action starts. Okay, so here you have got a message window, a progress window, a log window, and a table. And the thing what you have to see here is the convergence. Okay, so you are going to struggle with the convergence, and the only control you have is the meshing, right? Okay, so once done that, what I'm going to do is go to the study and say compute. Okay, so you have to bear with me, and I will hint to you something about how do you work to get a convergence. Okay, so I'll show you when the simulation starts what's going to happen. Okay, so the first point is VD equal to 0.8, VG equal to 0. Okay, so this is the first term. So now what do you see? Resultant estimate 2 e raised to 4, solution estimate 30. So these are kind of like errors, right? And these numbers should go down and keep going down and down. And this is damping, so we will not cover what that is, but hopefully you will see, or you will have to struggle. So either can happen. So when you see these numbers on residual as stagnant, means that you might have to struggle. So let me just stop it here because I know what's going on. So if you click here, the button says stop. Let me go here on the study, and let's do this from 1 to 1.2 and steps of 0.1. That's okay. And just save it and compute study again. If I have to struggle with convergence, I will put you on a hold and I will get the right settings on the meshing. So let's see what happens now. Okay, this is a very important part, that's why I'm covering it, the convergence, right? Should proceed, right? Why is it stuck? Okay, maybe I didn't hit, yeah, I didn't hit it properly. Compute. Okay, to assist your convergence, there are lots of settings here. And once you get used to this software, you will be easy to, for you it will be easy to do it. Okay, 2.3 e raised to 4. 6.3 e raised to 3. Residual estimate I'm reading. 6 e raised to 3. So let's look at this convergence plot. Okay, so this plot will keep on going down and down till the solution error becomes e raised to minus 6 or something like that. Okay, so now it is 6.5.1, again back to 6.3, 6.8, sorry. So let's see what this convergence solution estimate is going to do. Okay, so it's declining, so that's a good news. Okay, it has further declined. So when you reach a damping of 1, it's going to repeat the damping of 1 till these two factors go down to very small values. You see that? Okay, so it's 0.29 on the residue estimate. So it's done. So the first point is done. So you see how the error has dropped to 10 raised to minus 9 over here in the convergence plot. So now the next point is going to use this as the initial guess. So it will not try to converge from the scratch. So if you remember, it says last parameter here. So that's what it is doing. Otherwise, each one is going to take that much time. But now when you have the initial value, it's going to start with the initial value from the previous parameter, right? So now it's going to be fast. You see, the convergence is going to be faster. Okay. So what I expect to see is a typical. Let's see, is there a problem here? No. What I expect to see is a typical transfer characteristics. Okay, and then I'll show you the various regions of transfer characteristics, and I'll show you how the channel is formed. Right, so that is called inversion. Again, these terms, if they don't make sense to you, doesn't matter. You go to the playlist on analog integrated circuit design where I discuss the devices, and then you will know what I mean by channel inversion. Right, so I'll show you the channel inversion here. Okay, so let me put you on a hold till this simulation finishes. Okay, see you in a bit. Okay, so welcome back. We are done with simulation, and let me see. It took me 27 minutes and 23 seconds to simulate this. Okay, so now what you are looking at geometry, we are looking at the electron concentration and its flow later on. But let's draw a graph. So to draw a graph, you need to go to results, right click it. You can say sing one-dimensional plot. And your solution is specified over here for all VDs and all VGs, right? So again, you right click on this head and say global, and the global you are going to plot the terminal current. So you go to semiconductor under NMOS terminals, and we know that drain terminal is terminal 3. So if you click that, it's going to show up here, and then you can just say plot. Okay, so now what do you see? You see here for different VD, or 1 volt, 1.1 volt, and 1.2 volts. These are the three curves, right? And its turn-on voltage is going to be around 0.4 or 0.3, right? And if I was to put it on a log scale, so if I click here, I'll put this y-axis on a log scale. So what do you see? You see that you have around you can say 10 raised to minus 9, okay, is the subthreshold current. And then if you find out the slope in voltage per decade of the current, that will be called subthreshold. That will be called the subthreshold slope, right? And then over here you can see somewhere over here where this linear ends, that would be your threshold voltage. And after that, So let's move this legend so you can switch off this by this. After that, what you see over here is a mobility degradation. So let's put it again into linear scale. So you see that the slope is going up, and ideally it should go up as a square, but then it becomes linear, and then it becomes, less than linear, right? So basically it's going to just fall off, right? So what do you see? You see mobility degradation over here, and if I want to find out the slope over here in linear region, that will be my GM. This will be my your threshold voltage, and if you go way to the left, you are going to look at the sub-threshold leakage current, which is the cause of all the static losses in your gates, right? So this is your transfer characteristics for this MOSFET, right? And the currents are around 40 milliamps. Yeah, so the device size is 2000 divided by 40, so 2000, so 200 by 4, so that is going to be 50. So 50 is W by L in this case. Okay, so having done that, let's quickly, without wasting time, put in another study. Okay, so you can say add study. So what happened? I just said add study, didn't add study. Okay, let's do this again. Okay, it's over here. Okay, and you want to add additional stationary. So another stationary study here. So that comes up as a study 2. So what I can do is I can cancel this out. Okay, so on the study 2, you again go back to auxiliary sweep for all combinations. And here, this time, first thing I'm going to put is the VG part, right? Okay, so you add it, and instead of VD, you first put VG. And here, I am going to say VG goes from 0.2 to, in steps of 0.1, to something like 0.6, isn't it? Okay, so, or 0.7, for example. Okay, 0.7 is good. Okay, so VG is varying from 0.2 to 0.7 in steps of 0.1. Say add. Why is it red colored? Delete. Add. VG. Add. Why this would be red? What happened in the study 1? Stationary. This is not red here. Doesn't say what's there. Wrong number of arguments. Oh, maybe a typing mistake. Hang on. Yeah, a typing mistake here. This is not comma. This should be dot. Yeah, sometimes I do is typing mistake. And now it's okay. So for this different VGs, I'm going to do different VDs. So VD I'm going to take from 0 in steps of 0.05 to stop of 3 volts. I think that will be good enough. Right. And last parameter, and say auto. So we are done with this, but convergence is the issue, right? So I already figured out stuff here. So here I'm going to use another set of numbers. 30, 15, 1.08.9. 30, 15, 1.08.9, and 1.1, I think. 1.15. Let's verify that again. 30, 15, 1.08.9, 1.15. Okay, so this is my mesh. Build it. So slight variation in mesh, right? And I'm ready for the simulations. So this time for every VG, I'm sweeping VD. Okay. So I think auxiliary all combination last parameter auto 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and this will go from 0 to 3 and say compute. Okay, again observe the log, and if it doesn't, I'll put you on a pause and make it converge and come back. So I hope that it converges. Okay, look at the residue estimate. It's dropping. Now it's increased again. It's dropping. Okay, it's dropping. Look at the solution estimates or solution errors. Okay, still dropping. Okay, still dropping. So now the damping factor is 1. So it has still dropping. Okay, so first point converged. So now the initial guess is done. So remaining will converge. So what I'll do is I'll put you on pause and come back once the simulations are done. Okay, so it finished the simulation and I took 43 minutes and 29 seconds to finish this simulation. And let's go ahead in the study to plot the output characteristics. So it's going to be a 1D plot. It's going to be a second solution. And in this 1D plot, I right click and say global. And I choose here the terminal current from terminal 3 current, right? So I choose that and I just hit plot. Okay, let me see if I'm recording. Yeah, it is recording. Okay, so you look at this. If the colors are not clear, I can change the coloring, and there are presets for coloring here. Yeah, so I just made all of them blue. Or you can choose cycle reset, or you can choose cycle, whatever. So basically what I'm showing here, I'll turn off the legend. Okay, so I see here my output characteristics and of the device. And what do I see? I see in this chart, I'm going to see first velocity saturation on this side, and then I'm going to see the output impedance of the device, right? So this is that. Now there's few more visualizations which you can do, right? So I wanted to show you channel inversion. So if you go to results and if you go to animation and say player, so this will add animation. Okay, and here I want to go closer to this here, so that you can see it clearly, maybe even more. Okay, so this is from solution. This is from electron concentration from study 1, right? And here I'm going to loop over all VG for a given VD. Okay, and I'm going to put in, let's say, 30 frames, and let's say I want to display each frame for 1 second and say repeat. So you will see this, how this channel is formed, right? So right now this is VG of 2.4 and VD of 1.2. So the channel is well formed. But if I run play, so let it just create a movie. So you will see the formation of this channel. So the channel will start with the yellow color here because it represents less number of electrons. So there are no electrons in the channel. And then it will turn to red. And also it will not be flat, it will be have a triangular. If I see the cross section, it will be a triangular because there is a 1 volt drain voltage applied. So let's even zoom further if we can. Okay, let's even zoom further. Yeah. So now let's play this. So you see it starts with yellow, and see the formation of the channel, right? And the channel is not a flat line, right? So it's going to repeat. So right now VG is 1.2, 1.3, 1.4. So it's becoming thicker and thicker. The channel is becoming thicker and thicker, right? So that's what is happening with this. Right, we'll start again now. So it is you see yellow, and then the channel is formed. So this is basically the inversion which you are seeing. Okay, so I'm going to stop this and put one more animation. Okay, so one more animation. Animation 2. Player. And this time I'm going to use the other electron concentration. And here I'm going to see channel length modulation. So what I'm going to do is I'm going to choose a VD. Hang on. What? Just 1 second. I should have both the results, isn't it? So this is stored solution. This one. This is 3 voltages. How about this one? I should loop over VD for a given VG. Let's choose the second one. Loop over VD for a given VG. Okay, so let's choose a VG of 3, and VD is an entire list. Okay, so I am going to choose this with 30 frames, and I am going to repeat it with 0.1. Okay, and I am going to hit play. Okay, so you will see just start with a channel, right? So right now this voltage VD has to be close to 0, right? For a given VG. So VG I have chosen as 0.3. Yeah. So what do you observe here? So let's slow this down a little. Okay, so let's slow this down a little. Okay. Okay, so what you see here is it starts with the whole channel being red, and this portion you see is down, right? So I can pause in between and show you that. Okay, over here. So you see here the entire channel is there, and then over here in this portion you see the yellow color, right? That yellow color is going to increase and keep increasing, and the effective length of the channel is going to shrink. So you see the effective length of the channel is shrinking. Okay, so that's what is happening as I take VD up for a given VG, and you will also see that the depletion region over here is going to widen. Okay, so this yellow appearing is basically the pinch off. The channel pinch is off from the drain. So if I stop this and show you on VD equal to 0.2, it will be even clearer. And say hit play. So it will generate it again. Okay, so let's see what's going on in terms of pinch off, right? Okay, so you see the effective channel width is channel length is much smaller here, and the pinch off is much clearer here, right? So I think I have done that. There are other things which you can get from it, like you can plot the drain induced barrier lowering. You can cut sections into the geometry along a plane. You can cut the sections, you can have a cut line in 3D, and along the line you can plot the potential, basically just to show the barrier lowering and stuff like that, right? So here I am going to stop, but let me see. Okay, so that's a good gets a good picture. Yeah, so I'm going to stop here. And I hope you understood how the active devices can be simulated. You can do the same thing with diodes. You can do the same thing with bipolars. You can also do exotic devices like PHAMs here. You can do power devices like SCRs, TRIACs, DIACs, and things like that. So everything is possible. You have to just generate a structure, and you should do appropriate doping, and you should have appropriate boundary conditions, right? And you should have appropriate stimulus applied, okay, to those boundaries, and you will be able to see the physics, and you'll be able to get the VI characteristics, and you should be able to model it. Okay, so I hope I could introduce to you COMSOL, right? Thanks a lot. Thank you very much.